Hi there. In this video, we're going to talk about harmonic functions in the context of complex variables. You would have seen in your study of multivariable calculus that you can have a function of two variables x and y. It could equal to something, for example, x squared minus y squared. If we take the derivative, that's the second derivative of f with respect to x, and we take the second derivative of this function with respect to y, and if we add them together, then we get 0, okay? So this is called Laplace's equation. In this instance here, we can see that the first derivative, df dx is equal to 2x, and the derivative with respect to y, df dy is equal to minus 2y. And then we take the second derivative with respect to x, and we see that it's 2. And we take the second derivative with respect to y, and we see that's minus 2. And of course, if we add them together, the 2 and then the minus 2 added together give us 0. Okay, so that's Laplace's equation. So when a function has a Laplace's equation applied to it, it's called a harmonic function. So in this instance here, f is a harmonic function because this constraint, this condition, Laplace's equation is there. So how does this apply to the complex plane, and what does this have to do with complex variables? So we have seen thus far that we have a complex variable w, and it's equal to u plus jv, the real and imaginary parts. And we also saw that both u and v are functions of x and y. So this is the kicker, right? So if w is an analytic function, so we spoke about what analytic functions are in the last video. So if w is analytic, then u and v are harmonic functions. We can actually show that. So if w is if w is an analytic function, then u and v are harmonic. So we can prove that both u and v are harmonic by using the Cauchy-Riemann equations, which we had derived in the last video. So if we recall what those equations are, it's that dv dy, that's dv dy is equal to du dx. That's the first equation. If we find the derivative of both sides with respect to y, so we have dv squared and dy squared, that's equal to du dx and then dy. So the other equation in the Cauchy-Riemann set is that dv dx is equal to minus du dy. So if we find this derivative with respect to x on the left hand side, so we get dv squared dx squared equal to, okay, let me just write the minus on the other side and make that positive. So we have du dy dx. And what do we know about mixed partials? We know that mixed partials are equal. So that is equal to that, okay? So if these two are equal, then what's on the left-hand sides should also be equal. So what that means is that d squared v, dy squared is equal to minus dv squared dx squared. So of course this implies that d squared v dx squared plus dv squared dy squared is equal to 0. So we have shown that v is actually a harmonic function. So we can use the Cauchy-Riemann equations to also show the same thing about u. So all we would do is we would take u with respect to x. So let's do that. So if we take u with respect to x, then we have du squared, okay, then dx squared, that's the right hand side, here on the top. And now we do the same thing with the other side of the equation. Then we get dv dy dx. And then applying the other equation, we have minus du squared dy squared and that's now equal to day v, day x, day y. So these mixed partials must be equal. So the other side is equal as well. So that means that day squared u with respect to x and the second derivative with respect to y is equal to 0. So we have derived it in the exact same way. We can show this in a basic illustration. If we have w is equal to z squared minus 4, we have looked at this example several times now. So if we wanted to prove that this is a harmonic function, what we would actually do is we would firstly gather all the expressions in terms of u and v. So we would have x plus jy, this is the definition of z. We've substituted z. We expand that out, so we have x squared plus j 2xy minus y squared minus 4. We gather the expressions, so we have x squared minus y squared minus 4. Then we have plus j 2xy. So that means that u, that's the first part of the expression, is equal to x squared minus y squared minus 4, and v is equal to 2xy. So day u, day x is simply equal to 2x. The rest are treated as constants. And then the second derivative of u with respect to x is equal to 2. So we do the same thing with v. Day v, day x is equal to 2y. Remember that x is treated as the variable. And day v, second derivative with respect to x is equal to 0. Remember that, y is treated as a constant. So this entire thing is a constant, therefore it's equal to 0. So we can find the same derivatives with respect to y. So we have day u, day y, okay, here. So we see that this is minus 2y, and the derivative, second derivative with respect to y is equal to minus 2. We can immediately see that 2 minus 2 gives us 0. Remember that we have day squared u, day x squared, and day squared u, day y squared. So the sum of this 2 should actually equal to 0. So in the same way here, we can take day v with respect to y, and we can see that this gives us 2x, and then we find the second derivative, day squared v, day y squared, and this gives us 0. Remember that x is treated as a constant, so of course 0 minus 0 just gives us 0. So we have shown that for this particular example, that z squared minus 4, we know that it's an analytic function. We showed that in the last video. And we can see that since it is an analytic function, the second derivative with respect to y of both u and v give us 0, proving that both these are harmonic functions. So thank you for watching.